In October 2015, astronomer Tabitha Boyajian sent a paper to an academic journal that would make headlines around the world, not because she had solved a mystery, but because she couldn't. A star 1,180 light-years away had dimmed by 22%. No planet causes a dip like that. No known astronomical phenomenon did either. Something was blocking it, and no one could say what. In 2009, NASA launched the Kepler Space Telescope with a single mission: find planets around other stars. Kepler watched 150,000 stars simultaneously, measuring their brightness with extraordinary precision. The method was elegant. When a planet passes in front of its star, a transit, it dims the starlight by a tiny, predictable fraction. An Earth-sized planet causes a dip of 0.01%. A Jupiter-sized one reaches 1%. Regular, symmetrical, expected, but Kepler generated more raw data than any research team could analyze alone. So in 2010, scientists launched Planet Hunters, a citizen science platform where volunteers from around the world could log in, study light curves, and flag anything that looked unusual. Over 4 years, more than 300,000 volunteers classified millions of data points. Most were routine, but in 2011, several volunteers independently marked the same star with an annotation that would become famous in its own right: WTF. Officially, WTF stood for Where's the Flux? The star's formal designation was KIC 8462852, a catalog number from Kepler's field in the constellation Cygnus. Tabitha Boyajian, then at Yale University, took it on as a research subject. What she found defied every standard category. KIC 8462852 is an F-type star, slightly larger and hotter than our Sun, located approximately 1,180 light-years from Earth. It had burned steadily for billions of years, but between 2011 and 2013, its light curve showed events unlike anything in the database: dips of 0.5%, then 2%, then 15%, then 22%. These were not the clean, symmetrical periodic signatures of planetary transits. They were jagged, asymmetric, and completely unpredictable. Some lasted 3 days, some lasted a week, some clustered in dense sequences, others arrived isolated years apart. And there was one more anomaly, one that would become arguably more troubling than the dips themselves. The star appeared to be slowly fading, not just in short bursts. Across the entire 4-year duration of Kepler observations, the baseline brightness was measurably declining. Boyajian's paper landed in the astronomical community like a flare fired into a dark room. Every researcher who read it tried to generate an explanation. None succeeded cleanly. The first candidate was instrument error. Kepler's photometers had known quirks, but the dips appeared consistently across multiple independent detectors, and ground-based telescopes confirmed them independently. The hardware was fine. The star was not. The leading early hypothesis was a dense family of comets, perhaps thousands of them, orbiting in a chaotic cloud. As they transited the star's face, the argument went, they could produce irregular, asymmetric dips of varying depth. The model had some appeal. Comets carry dust. A large enough swarm could, in theory, produce the observed patterns. But the 22% dip was a problem. For a comet cloud to block that much starlight, it would need to encompass an extraordinary volume, something never observed around any star in any galaxy we have catalogued. And then there was the secular dimming. In 2016, Louisiana State University astronomer Bradley Schaefer analyzed photographic plates from the Harvard Observatory archive. Images of KIC 8462852 dating back to 1890. His conclusion was striking. The star appeared to have faded by approximately 20% over the past century. A comet swarm does not explain a star dimming over 130 years. Whatever was causing the transits, something else appeared to be responsible for long-term fading. The photographic plate methodology was immediately contested. The debate has not been fully resolved. On October 15, 2015, 1 week after Boyajian's paper appeared publicly, Penn State astronomer Jason Wright did something that almost never happens in mainstream astrophysics. He filed a document formally proposing that the anomalous light curves of KIC 8462852 were consistent with the orbital signatures of alien megastructures, not as a fringe theory, not as a thought experiment, as a legitimate scientific hypothesis, submitted to a peer-reviewed journal and accepted for publication. The specific structure Wright proposed was a Dyson swarm, a network of enormous solar energy collection devices built in orbit around the star by a technologically advanced extraterrestrial civilization. Such structures, he argued, would orbit irregularly, create asymmetric transits of unpredictable depth, and produce exactly the kind of light curves Kepler had observed. The response was immediate and global. Within 72 hours, KIC 8462852 had a new name, Tabby's star, in honor of Tabitha Boyajian. Articles appeared in The Atlantic, the BBC, the New York Times, Wired, Scientific American. NASA issued statements. The SETI Institute directed the Allen Telescope Array at KIC 8462852, scanning for artificial radio signals. None were found, but the absence of a signal, Wright pointed out, was not conclusive. A civilization capable of building a Dyson swarm might not be transmitting in frequencies we scan, or at all. The counter-evidence came from an unexpected direction, light itself. In 2017 and 2018, Boyajian's team mounted a coordinated observation campaign, funded in part by a Kickstarter campaign that raised over $107,000 from 1,962 public backers. During new dipping events, they measured the star's brightness simultaneously across multiple wavelengths: ultraviolet, visible, infrared. If a large solid object, a planet, a spacecraft panel, were blocking the light, the dimming would be wavelength independent. Blue light and red light would disappear at equal rates. That's physics. What they found was the opposite of uniform. The star dimmed more strongly at shorter wavelengths, ultraviolet, and less at longer infrared ones. This is the fingerprint of dust, fine semi-transparent particles that scatter shorter wavelengths more effectively than longer ones. A Dyson panel made of metal or composite material would not behave this way. The 2018 paper was widely interpreted as the strongest evidence yet for a natural explanation: circumstellar dust clouds, likely from a disrupted comet or asteroid. The megastructure hypothesis took a significant blow, but the secular dimming, the century-long fading, remained unexplained, and no complete model has yet accounted simultaneously for all three phenomena: the deep transits, the multi-week dipping events, and the long-term baseline decline. The astronomical community has, broadly, divided into three positions. The majority now accepts circumstellar dust as the primary explanation for the dipping events. The 2018 wavelength data is compelling. The specifics remain open: what kind of dust, where it originated, what object was disrupted to produce it. But the mechanism is natural, physically plausible, and consistent with the observations we can directly measure. A second group accepts dust for the dips and insists the secular fading requires a separate explanation. The star appears to be losing light on timescales of decades to centuries. That is not what transient dust clouds do. This group calls for extended multi-wavelength observation before any definitive conclusion. The secular dimming needs its own explanation, whether that's an unusual stellar interior, a large orbiting body gradually depositing material, or a calibration issue with the oldest photographic data. The third position is held by a smaller but vocal contingent, including Jason Wright himself. Wright has publicly stated that dust is now the most parsimonious explanation for the dipping events. He has also publicly stated that the secular dimming is genuinely mysterious and that closing the case prematurely, while the data remains incomplete, is not scientific prudence. It's wishful thinking. The SETI community draws a broader lesson. The value of Tabby's star, several researchers have argued, is not that it probably harbors alien technology. It's that it demonstrates exactly why the search for technosignatures must be continued. Because the universe occasionally produces phenomena we cannot explain. And those are precisely the moments that require the most sustained, careful attention. There is historical precedent. In 1967, Cambridge postgraduate student Jocelyn Bell Burnell detected a radio signal so precise and regular that she and her supervisor initially labeled it LGM-1, Little Green Men. The signal turned out to be a pulsar, a rapidly rotating neutron star that had never been observed before. The alien hypothesis was discarded. What replaced it was a discovery that reshaped our understanding of stellar physics. No one is seriously arguing that Tabby's star is surrounded by alien construction, but the intellectual honesty of science requires acknowledging we don't fully understand what is happening there, and perhaps that is worth more in the long run than a tidy answer that closes the file too soon. Tabitha Boyajian continues to study the star. Her team publishes follow-up papers as new dimming events occur. In a nod to the citizen science community that first flagged it, each new dip has been named after an archaeological site: Elsie, Celeste, Skara Brae, Angkor. New observations continue. The Las Cumbres Observatory Global Telescope Network maintains a continuous watch. The James Webb Space Telescope has been turned toward KIC 8462852 for targeted infrared studies. But here is what remains true as of now. Of the 150,000 stars Kepler observed across 4 years, not one produced a light curve like Tabby's star. Not one. The dips are real. The secular fading is contested, but present in the data. The dust hypothesis is compelling but incomplete. No published model accounts simultaneously for the deep transits, the multi-week dipping events, and the long-term baseline decline. In 2025, a major motion picture brought the concept of an alien organism systematically depleting a star's energy into global cultural consciousness. Project Hail Mary's astrophage was fiction, but the story it prompted millions of people to ask about, is something really out there consuming a star's light? Was not. Tabby's star is real. The 22% dimming is real. The peer-reviewed paper proposing alien megastructures, published in a legitimate journal by a mainstream astronomer after passing scientific review, is real. This is not fiction. It is not science fiction. It is a real star, 1,480 light-years away, still being watched, still dipping, still not fully understood. In astronomy, the most interesting objects are usually the ones that break the models. Black holes broke the models, pulsars broke the models, dark energy broke the models, Tabby's star broke the models, whether it broke them because of circumstellar dust, or a disrupted asteroid belt, or an unusual stellar interaction, or something else entirely. That answer remains open. Some questions in science stay open for years, some stay open for centuries. This one has been open for 10 years. The light is still fading.